Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And today we have a duet. And I'm very happy to have Xiang-Yu Li and Lars Mattsson with us today. Hey, Xiang-Yu. Hey, Lars.
Hi, Frank.
What's your geolocation, Xiang-Yu?
I'm now at Richland in Washington State, USA.
Oh, okay.
And I'm now working at the Pacific Northwest National Lab.
Great. When did you start that position?
I started right at the lockdown started in Washington State. That was in March 2019.
Okay.
Yeah.
Very good. How about you, Lars? Where are you at? 2020. Yeah.
Yeah, I'm normally in Stockholm at the Nordic Institute for Theoretical Physics, NORDITA, which is part of Stockholm University. But during the circumstances right now, I'm residing near Uppsala, where I live, actually.
Okay.
So, yeah.
Well, if that's where you live, that is a pretty awesome library there behind you there.
Yeah, this is my home library.
Pretty
I'm
cool.
sitting at home right now.
Those are all astronomy books?
Not all of them, but quite a number of them, actually. Yes, I was collecting books for a while.
Very cool. Very cool. So what do you guys like to do for research in general? Lars, why don't you start? What do you like to do for research?
Well, I think the paper here will show some of it, actually. What I do is a lot of computational astrophysics, simulating turbulence, and cosmic dust has been sort of a main theme throughout my whole career. I started working on dust-driven stellar winds, in fact, simulating those, and then I moved on to look at dust in the more, in the grand scheme of things, you can say. And these days, I'm mostly interested in what's happening in the interstellar medium. And being something of a theorist, I do a lot of numerical work on that.
So I'm always curious how people get into the fields they do, given that there's a universe of choices, so to speak. So how did you get into dust, Lars?
Well, like I said, I wrote my PhD thesis on dust-driven winds, and that's where it all started. So the basic problem there is particles in flows, which is a sort of a classical theoretical physics problem. And I kept on doing that, but in other contexts, you can say. So that's how I ended up with this. And yeah.
Okay.
I think it's more or less accidentally. It's not like I planned to do cosmic dust, because I've always been interested in cosmic dust. It just happened.
Yeah. How that? Okay. Very cool. Xiang-Yu, what do you like to do for research?
So in general, I'm really interested in theoretical physics. So now I'm working on the intersection between atmospheric science and astrophysics.
Okay.
So because they have a common problem that haven't been solved, that is the turbulence. So I started working on the turbulence when I was an undergraduate student, and I took the course fluid mechanics, and my lecturer told us that it is one of the most difficult and classical questions in physics. So I started my master after that, and working on the convection flow in the laboratory. I tried to design instruments to drive a thermally driven convection fluid, and try to measure the temperature and the velocity. After my master, I started to think about more theoretical work. So then I went to NORDITA, where Lars is working now, and there I started to work with Axel Bradenberg. So he's my thesis advisor, and he's working on the astrophysics in general, gravitational waves and astrobiology. And he brought me into the simulation of the turbulence and the particles in turbulence in general. And then I started working on the formation of the cloud droplets in our clouds, like over there in the sky. So because it's also a problem of particles in turbulence. And meanwhile, I was really interested in what Lars was working on back then. He was working on the dust grains in the interstellar turbulence. And when I look at the equation, I was, wow, gosh, they're so similar. You know, we should do something together. So that's how we start to work together. I think almost close to the end of my PhD, because I had more time to explore more broad fields in astrophysics.
Cool. Very nice. And that is going to take us to this really lovely article.
Oh, thank you.
This is an APJ. It's an open access, so anybody can get the full real deal now. Dust growth by accretion of molecules in supersonic interstellar turbulence. And Xiang-Yu and Lars, take us away.
Yeah, should I start with say something about the background here, because there is a bit of a background on this paper, because it started with an analytical theory that I was developing a couple of years back, which relies on a very simple idea that the growth rate or the growth velocity of cosmic dust should basically be proportional to the density variance of the carrier medium in which you have your growth species also.
Okay.
And this sort of followed my philosophy in working with theory, that you should break down things into bits and pieces, break down the problem to simple ideas which you can handle more or less analytically, or in easier pieces. And doing that, I found a way to build a theory for this particular part, and then I realized that this had some interesting consequences, and that we also needed to simulate some of this in order to confirm it, and also explore the limits of my simplistic mathematical theory. And while doing this, I also kept on developing another idea that something must happen to the size distribution of these grains due to this density variance thing. And I was working on an idea of using and simulating the growth as an Ornstein-Uhlenbeck process, which led to a certain connection, a broadening of the grain size distribution, but also a very tight connection between the density PDF of the medium and the grain size distribution.
Okay.
And again, we felt that Xiang-Yu was at that time, I think he discovered that before I actually finished my theory, and then we realized that we had to test this thoroughly and write a paper about all of this. So that's the background of this paper, basically.
Cool.
And yeah, why don't you start now, Xiang-Yu, and walk us through the paper?
Right. Thank you, Frank. Thank you, Lars, for the nice introduction. So in this paper, we, as Lars emphasized, we made it what to test Lars' theory that he developed a couple of years ago about how the dust grows in the interstellar turbulence, because the interstellar media is highly turbulent, and the Mach number is pretty high, around 10, which means it is very compressible. But in most of the work that we had before, is that we treat this turbulent environment as a homogeneous environment, which means we didn't really consider the variation of the gas density in the simulations. And so that's the motivation that we really want to check how the compressibility of the flow affects the growth of the dust grains, and also to examine how the size distribution of the dust grains evolves.
Yeah.
So with that, what about we review the theory of Lars? That should be, yes, in section 2.3, accretion of the gas molecules on dust grains. So we have many physical processes that contribute to the growth of the dust grains in the interstellar medium. And one of them is accretion, which means that when the dust, they travel around in molecular clouds, then the molecules will just accrete on the dust grains. So that can be described by considering how the molecules condense or accrete on the surface of the dust grains. And that's why in equation 14, we have an expression for the surface area of the dust grains. As you see, A is radius of the dust grains. And when they stick to the dust grains, there is a sticking probability that is S. And it also depends on the mass fraction of the relevant growth species molecules. That's why we have Xi. And so there is another factor, is the thermal velocity of the molecules. And it is also proportional to the density of the gas. So that's why we have this simple equation for the mass change rate. And so based on this equation, then we have a relationship between the mass of the dust grains and the radius, and therefore we can reach equation 16 here. So here we see that the evolution of the radius of the dust grains, they are proportional to the density of the gas. Therefore, we need to solve the equation of the density, and then we can obtain the growth rate of the radius. And so to do this, Lars proposed a statistical description of the gas density because it's very difficult to have an analytical solution for the gas density because of the turbulence. And so if we look at equation 18 here, right, so Lars proposed that if we apply this spatial mean approach, assuming a periodic boundary conditions, we can see that the evolution of the spatial mean of the radius is proportional to the second moment of the gas density, as we show here.
Yep.
Right.
And variance.
Yes, basically the variance of the gas density. And so at this step, we still don't really know, for example, how this dAdt depends on the Mach number, for example, because Mach number is the parameter that can describe how compressible the flow is. And if you look at equation 19, and yes, here we go. So we can express this standard deviation of the gas density in such a way in equation 19. And there are many simulations about the compressible flow in the past. And there you can reach an empirical relationship between this between the standard deviation of the gas density and the Mach number. But they are empirical, so we try to not emphasize these empirical relationships. Instead, we just check how the evolution of the dust grains depends on the variance of the gas density. So to do this, we can go back to the Navier-Stokes equation, where we can get the gas density there.
Yes.
So that should be the first equation, I think. And then
I want to go up to one. Okay. Yep.
Yes, the first equation, the Navier-Stokes equation.
Yep.
So we solve this Navier-Stokes equation. We get the flow field U, and also we get the gas density, right? And so this is the flow, and because we consider the dynamics of the dust grains in the compressible flow, and we also solve the momentum equation for the dust grains as well. And because the dust grains, they have inertia, they may decouple from the flow field, and that's why we introduce this stopping time, tau. So the stopping time is a time scale to characterize the inertia effect of the dust grains that are moving around in the molecular clouds.
That's equation 12.
Okay, that's equation 12.
Yep.
So this is the stopping time is proportional to the density ratio between the dust grains and the gas, also proportional to its radius.
Mm-hmm.
And this term, the square root term, is just because of the because that when the dust grains move in the molecular clouds, there is this Reynolds number of the dust grains, which introduced this extra term. Right. So because of this stopping time, we have this Einstein drag term in the equation that is described by equation 11. Right. So now we have all the equations that to be solved, and then we can obtain the evolution of the size of the dust grains. Therefore, we could test the theory that was developed by Lars. Could we go to the figure 1 to check the time evolution of the dust grains?
Going to be done with the pencil code.
Yes.
Important to mention, yes.
Yes.
Give him a plug.
Yes.
Give him a plug.
Yeah. So here we show the structure of the flow for different Mach number. So if you look at the Mach number 1.38, that is roughly transonic regime, and we go to the supersonic regime and further to hypersonic regime, and we see here that the structure is very intricate, and especially the Mach number field, the local Mach number field varies quite a lot. And if you look at this hypersonic regime, like Mach number equals to 11, you see extreme large values of the Mach number, which shows very strong compressibility. So the regional Mach number could reach about 24. And this means that we can't really ignore this compressibility in the simulations of the evolution of dust grains. And also the corresponding density of the gas also varies a lot. You see very obvious filaments for the large Mach number case.
Mm-hmm. Mm-hmm. Oh, and just to be clear, these were these are 2D slices through a 3D simulation.
That's right.
Yes.
Yes.
Okay.
Yeah. And then if you look at the third panel of figure 1, you see this clustering of the dust grains.
Yeah.
Yes. Because of the structure of the gas density field.
Mm-hmm.
Yes. And so from this figure, we can already guess how the Mach number could affect the growth of the dust grains because of the spatial variation of the density field, as which results in the spatial variation of the distribution with dust grains.
Yes.
Right. And then if you go to figure 2.
Okay.
Right. Here we show the spatial mean evolution of the dust grains. And so the solid curves are the simulation results using the pencil code. And the dashed ones are the corresponding theory from Lars.
Okay.
And if we look at the lower Mach number cases, for example, the case for 1.38, and we see the two curves basically collapse on each other, which means that for low Mach number, the theory of Lars agrees very well with the simulation results. But as we increase the Mach number to, for example, to the supersonic and hypersonic regime, and we see that the theory deviates from the simulation results. So this is because for Lars' theory, it assumes that the dust grains, they're moving together with the gas. So they do not decouple from the gas. But actually, as we discussed before, that the dust grains, they have inertia, right? So their trajectory actually deviate away from the trajectories of the tracers. And that's why when we increase the Mach number, you have a larger velocity of the dust grains. And that's why the theory deviates from the simulations. And the decoupling between the dust grains and the gas is actually shown in figure 3. As you see, the URMS is the velocity of the gas, and the VPRMS is the velocity of the dust grains. And so the solid lines, they are the velocity of the gas, and this dashed lines, they are the velocity of the dust grains. As we see that if you increase your Mach number, the decoupling between the gas and the dust grains just shows up. So that is one reason that the theory deviates from the simulation results. And also, if we go back to figure 2, we see that this spatial mean growth of the dust grains, they are almost linear as a function of time. That's because if you recall the equation that proposed by Lars, this spatial mean growth of the dust grains, they're proportional to the variance of the gas density. And we show in figure 2b that the variance of the gas density reached a stationary state for different Mach number. And that's why we see this linear growth of the spatial mean of the dust grains. Okay. Right. So this means that this statistical theory of Lars indeed works and has the limitations for higher Mach number. And another aspect that is really interesting, as Lars and myself has also emphasized, is that the grain size distribution is very important for the stellar light, for example, for the coagulation process of the dust formation. And therefore, we also examine the size distribution and its evolution of the dust grains. And so here we show the size distribution for different Mach number. And we started with a monodispersed dust grains. So that we have the same size for all the dust grains. Then as time evolves it develops such a shape. And eventually, for example, if you look at the last few snapshots, you see a almost log normal distribution from a initially monodispersed size distribution. And it's very interesting that for the same Mach number simulation, the width of the size just increases with time. And this we also show in figure. The next figure is figure 5. Right here we show for a single Mach number, you see as time evolves, the width of the gray size distribution increases with the time. Imagine that if you have a case like a homogeneous flow field without turbulence, right? And the sigma A should be 0 basically.
Yeah.
So you won't see this like a broadening of the size distribution if you don't consider turbulence.
Mm-hmm.
And also if you increase the Mach number, as you see, this sigma A really increases dramatically, which means in the transonic regime or in the hypersonic regime, the broadening of the size distribution varies a lot. And that's why it's really important to consider this compressibility of the flow when you study the growth of the dust grains. And we have mentioned that we started with the monodispersed dust grain size distribution, and we reached a log normal distribution. So we were wondering if this log normal distribution of the dust grains are universal or not. So then because that's very important, because then you can parameterize the size distribution of the dust grains, right? In the more like complicated simulations involving more process like coagulation or other processes. And therefore, we also examine a case with this very canonical MRN initial distribution with a slope of -3.5, this power law distribution.
Right.
Then we started with this distribution. Then we track the evolution of the size distribution, and eventually we again get a log normal distribution.
Yes.
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 So then we are very curious why it is the case.
Yeah.
And then we start to examine the distribution of the gas density, because from the theory of large, we know that this the evolution of the spatial mean of the dust grains, they are proportional to the variance of the gas density. Mm-hmm. So we thought that could be the reason, and therefore we checked the distribution of the gas density, and it is indeed a log normal distribution, and that has been observed in other numerical simulation studies. So that's why we don't show it here explicitly, but they largely developed a theory to explain the link between the log normal distribution of the gas density and the log normal distribution of the dust grains.
Yes.
And maybe Lars can say something on the theory of this.
I mean, again, it's a rather simple idea. I said before that I modeled this as an Ornstein-Uhlenbeck process, which sounds very complicated, but the basic idea is very simple. You have high density regions where grains grow fast, and then you have low density regions where grains go slowly. And that means after a certain time, the growth of the grains will actually, or actually then this, if you start from a uniform, no, sorry, monodispersed initial condition, after some time you will have a distribution that actually reflects the statistics of the carrier medium where you have your growth species in that case. So grains that have been residing mostly in low density areas, regions will be small, while the ones that have been in high density regions will be large. And of course, if you think about it, that must reflect the PDF of the gas here.
Yes.
So I mean, it's rather simple actually, but when you see it at first, it's like, what? How did this happen? But it's quite cool. I mean, it's just logic. Yeah.
Yeah, it makes sense once you walk it through, but I agree. At first you go, why would that be the case? Okay.
Yeah.
Very good. Very good.
Yeah.
Continue.
Yeah. So okay. So these are the main results that we have for this study, and so here I also want to mention some like assumptions or limitations of the work, so we can open the door for the future exploration of this study. So, for example, we neglected this depletion of the dust grains.
Yes. Depletion of the molecules, you mean?
Yeah, the molecules, because here you see in that equation we don't have the sync term.
Correct. Right.
Right.
It was only a positive term. Right.
Yeah, precisely. So that's that is something we are working on now. But
also explain why this is why we left it out, because it seems like why didn't you consider depletion as such an obvious thing that must happen? And the reason is that it's numerically very complicated when you do full 3D turbulence simulation following lots and lots of dust particles as in Lagrangian particles in the simulation. It gets computationally very difficult to handle this in a parallelized simulation. A lot of communication, and it's not easy how to handle that. So we just decided that we'll leave it for now and see if we can find a smart solution later. It also turns out that this is only an issue if you run the simulation for very long, or when you get to very, very high Mach numbers where the density variance is large, and where you can imagine that after a while you will simply have grown the grains a little too much. So you shouldn't run into the depletion limited regime. But for lower Mach numbers, I think you can run the simulation for quite a while, and it's basically okay. I explore this in my more analytical paper, and you can see that qualitatively speaking, there's not much happening. It's just that everything slows down, and eventually the growth will stop because you run out of molecules that you can accrete.
Okay. Cool.
Yes. So right. So and also here we don't have a magnetic field right now, because that could be important for the charged dust grains. That is something that we are working on now. But and also, as there is a general bottleneck for DNS, right? The Reynolds number is low, so that is incomparable with the observed Reynolds number in the interstellar medium. Right. But nevertheless, I think this work really show that there is another source of for the growth of the dust grains, that is compressibility of the turbulence. If you take that into account, for example, from the transonic to the hypersonic regime, you can roughly get enhancement about 10 times for the growth of the dust grains. Therefore, we should really re-examine the source of the power for the growth of the dust grains. For example, that like previously people have proposed this supernova explosion, say that that is you can generate a lot of a lot of materials for the growth of the dust grains, but also when you have the supernova explosion, you could have this destructive effect, right?
Yes.
Yes. So so in this study really indicated that we should consider the compressibility of the turbulence very seriously. Mm-hmm. And also, as we discussed here, that we show this log-normal distribution of the grain size grain size. So if in certain way this can be observed, it will be really great, because then we can parameterize the grain size distribution by this log-normal distribution in other complicated cosmological simulations, for example. Mm-hmm. So that is 2 points that we want to convey for this study. And of course, here we haven't really considered magnetic field and fragmentation and depletion. So as Lars has emphasized as a beginning, that the philosophy of our study here is we want to focus on each physical process carefully and use the most advanced theory or numerical techniques to make sure that we have a solid theoretical understanding for each physical process. For example, for accretion, for coagulation, then we can eventually, our aim is to add all these processes together such that we can have a more comprehensive simulation of the growth of the dust grains and so on. Maybe Lars can comment more on this.
Sure, I can do that. Well, you said something about philosophy here, and if we can maybe enter into some more general discussion here about future and what we can, how we can go on. I like to distinguish between sort of the top-down approach and the bottom-up approach when you do numerical experiments in astrophysics, not only in astrophysics, of course, but in general. And the top-down, when I use that phrase, what I mean is that you try to make this grand simulation of everything. Mm-hmm. And then in order to do that, you have to make approximations, you have to have recipes and prescriptions for a lot of things that you want to include. And you take what you have and you just throw it all into your computer code and then you run, more or less. And of course, this is a way to do it, but the problem is that then you have to work your way down and try to improve on all the bits and pieces that you have in your model. And this is not easy, and it's not easy to know whether you got it right to begin with, or which part is wrong and which part is more wrong than the other parts, and so on. So the other approach is then bottom up, and doing what I said before. You break it down into pieces, and then you try to focus on each and every one of these pieces separately and try to understand it. And then you, like Xiang-Yu said, you piece them together, build your model, build your theory of, well, for example, the processing of cosmic dust by assembling these bits and pieces to something bigger. And doing it that way, I think the risk that you will misunderstand some part of the physics is less than if you do the other way. On the other hand, you're not going to do as fancy simulations as you would if you do the top-down approach, where you try to throw everything in and you can simulate something that and produce observables and all that, which I think is what people like to do. But there's different philosophies, and we have embraced this bottom-up approach.
Right. Yeah.
Well, it informs the, usually people invoke some sort of a subgrid model at the larger scales, and so these, if you like, microphysics calculations help inform those subgrid models. So,
yeah.
So speaking of the future, when these were 1024 cubed calculations.
Yes.
Would one expect new regimes to be uncovered if you went to 2048, 4096, etc.? Resolution?
Not much, I think. If you really want to get to the small scales where a lot of the interesting things happen when it comes to dust, you have to go to scales which are much smaller than the typical scale of a molecular cloud. I don't remember what was the physical scale we anticipated for the box here. Xiang-Yu, do you remember?
You mean the integral length scale of the turbulence?
Yeah, exactly. What was the integral length scale? Remember what we said?
Oh, that is for the
Was it
let's say
10
the Reynolds number.
No, but what was the physical scale? Was it 10 parsec or something that we said it was roughly the
Yeah,
simulation
something like that.
something of that size? We talk
Yes.
about parsec anyway. So if you really want to resolve something interesting, you have to go many orders of magnitude down.
Right.
And I don't think I don't see how you can reach that unless you, like you said, do a subgrid model of some kind, or zoom in and do something smaller. I mean, same resolution maybe in terms of the number of grid points, but you change the physical scale of the simulation to simulate something different in that sense.
Yeah. So I can follow up on these comments. I think if you look at this compressibility of the flow that is characterized by the Mach number. So now now we can reach a Mach number about 10. That means that the flow is highly compressible. We have this like a large variations of the gas density. So if the observational data, the indication from the observational data show that the Mach number is about 10, so which is just within our reach.
Yeah.
And we're not entirely sure about the number, of course, but then we can say, okay, we can conclude that this compressibility of the flow is already captured. That results in this variation of the density. The only thing I can think of now is that how the large Reynolds number, because we have can really affect this result. That's as mentioned, if you push to 2000 cube simulations. In that case, you could introduce more intermittency of the turbulence with a higher Reynolds number. So that may change the behavior of the gas density.
That's a good point. That's
Yeah.
a good point. I think the Reynolds number that we can reach here is of the order of a few hundred, depending on how you calculate your Reynolds number.
Yes, that's right.
Yeah.
Yeah.
But,
So.
But if you want to get perspective on this, I can quote Ralph Plessen once said that what we typically do in this business is that it's like we're trying to simulate the water flow using honey as a proxy for water.
Yes.
That's kind of what we do when we run these simulations, say this is interstellar gas, because the interstellar gas has a Reynolds number which is, well, of the order 100,000 or probably more than that.
5 to the 6.
But we can reach a few hundred, maybe 1,000 at best. But it's true that if you increase the resolution of your simulations, so if you go to a box with, say, like, I don't know, 4,096 cubed, for example.
Right.
In that case, we could increase the Reynolds number by a factor of 2 or 3, maybe, or something like that. But you're still not.
Right.
You're nowhere near the real number, the Reynolds number. No.
Indeed. Yes.
All right. Awesome work. Seems like there's a lot of fruitful directions one can take this over the next few years, from maybe some observations of grain size distributions to including grain depletions to magnetic fields to resolution Reynolds number effects. It's all fairly cool. So Xiang-Yu and Lars, I want to thank you so much for spending some time and walking us through your your really lovely article here today.
Thank you. Thank you for inviting us.
Thank you, Frank, to have us here.
Sure, pleasure. All right, everyone, we'll see you on the next one. Bye-bye.
Bye.
Bye.